However, sometimes they may only ask you to calculate some member forces instead of all member forces. And if that's the case, if you want to use a metal joint, you can still solve the problem, but it takes maybe 2 hours. If you are using another method, which what I call the method of sections, with the second method I'm talking about, then you can get the problem done in maybe 10% of time. Okay? And that's the method I called, or the book called method of sections this time. The fundamentals are still the same thing. Every time when we solve problems, we use Newton's first law, in fact. All the chapters, right? We basically use a Newton's first law. Now the question is how we are going to apply Newton's first law to solve this kind of truss structure, but we're only interested in calculating some member forces. Okay? And that method is called the method of sections. So you still need to make a cut. But this time, we're not going to cut all the members surrounded with a joint. We're going to have a strategic cut. We call it smart cut, so that we can solve the problem. Okay, going back to look at this structure, for example. I guess this is the same structure, right, as we had with this one. Same one? At least very similar, okay? Different, a little bit different, okay? Let's go this way. That's fine, it's similar. Now, just in case, you need to calculate some of the member forces. Let's say you are interested in calculating the member forces, member force BD, member force B, and then member force C. For example, you are interested in calculating these 3 member forces. You use a metal joint, you can solve the problem. It's okay, but it takes longer time because typically you have to start from this point and step by step. If you are only interested in calculating some, then what you need to do is just to cut those members directly. But still, from the first step, in general, you need to look at the entire structure first and then to calculate the reactions. That's in general, because most problems does require you to calculate the reactions anyway. So let's say we're done with the first step. In other words, we know these reactions. So it's very easy. You just plot the entire structure, and this the pin, cut the pin, you gave 2 reactions, and cut this roller E, you gave another reaction with all 3 forces. You collect all the forces in x direction equals 0, you collect all the forces in y direction 0, and then you take a moment equation, and that's equals 0. Combining those 3 equations, in general, you can calculate those 3 unknowns from the support. So that's the first step. Assuming we're done with that step, we need to move to the next step, which is to calculate those member forces directly. Then what you need to do is you just make a cut for those members you are interested in calculating those forces. Then what? When you have a knife to cut completely, you must cut completely so that the structure will separate into 2 parts. You must make a complete cut so that the structure will split into 2 parts. This is the left side and this is the right side. And it's really up to you to pick any side. You pick a simple side with less force involved. For example, when you make this cut, you are looking at the left side. Then what? This whole left side must satisfy the Newton's equations as well. Because otherwise, this one will not be staying there. So, when we make the cut, I'm going to plot the left side, which is still this part of structure. I'm going to plot A, B, C here. You may say, well, I cut in the middle, then why I do not? You can plot this using blue line, doesn't matter. Okay, so let's plot this a little bit, plot this one a little bit, and then plot this one a little bit. That's fine. Then, when you make the cut, originally there's no internal forces in this point, but you make the cut, it's separated, then you need to give a force acting at joint B and going to this direction. Because we do not know whether this FBD is in tension or in compression, we are always assuming it is in tension. That's our assumption. So if it's in tension, then we're always plotting this force leaving that joint. It doesn't matter, you apply here, doesn't matter, just in this direction. Similarly, you also cut this member, it's called the BE, you cut it, you gave another force leaving this joint as well. And then you cut CE to make a complete cut. And then, of course, you need to provide with another force. It's called FCE. Okay? So you are looking at the left side. Then, obviously, left side has P1 here and then has P2 here acting on point A and point B, respectively. Now, this is, again, is what we call the free body diagram. Whether you're going to shade this in between, it doesn't matter. You really do not need to make this one blue because there's no material here. I don't know why. You don't need to worry about anything inside. This is empty, in fact, right? Okay, so this is called the free body diagram. And this is the free body diagram with respect to part of rigid body. It's not with respect to only one joint. There's a lot of joints. So then what? That's a typical two-dimensional free body diagram. If that's the case, then obviously you can collect all the forces in x direction, which must be equal to 0. That's the first equation. You collect all the forces in y direction. It must be equal to 0. That's the second equation. And you take a moment equation. You take a moment at any point you like. You can take a moment at point A, or point B, or point C, or even the virtual point E, which I'm going to show you why we need to choose point E, because that's easier. Okay? So in general, you have 3 equations, right? You have 3 equations for this problem. Let's now calculate. Let's count how many unknowns for this problem. How many unknowns for the problem? 3. That's exactly what you are writing. FBD, FBE, and FCE. These are the only 3 unknowns. You may wait a second. For forces, each force should not have only one unknown. Well, the directions of those forces are given. So only the magnitude of each force is unknown. So this force, you only do not know the magnitude, which is called FBD. That's one unknown. This force, you know the direction, because this is the direction. You know the direction. So then only the magnitude of this force, we call FBE, is unknown. So the second unknown. And then for this force, the direction is given as well. It's horizontal. Only the magnitude of this force is unknown. So that's the third unknown. 3 unknowns. We just mentioned there are 3 equations, right? All the force in x direction equals 0. All the force in y direction is 0, and the moment equation. That's 3 equations. You combine those 3 equations, in general, you can solve for those 3 unknowns. And that is called the method of sections. Of course, I'm using this example. In reality, you can make any cut you like. The bottom line is to try to solve the problem. For example, if you are interested in calculating those 3 members, but you want to make this cut in this inclined direction, it doesn't solve your problem. I'm not saying when you make this cut, is there anything wrong? There's really nothing wrong. But you cannot solve the problem. So if I'm asking you to calculate some other member forces, then probably you need to cut in other directions. Because if I'm not asking you to count those 3 members, you cut it like this way, it doesn't solve your problem. So that's why I call this cut, it's a kind of strategic cut. You need to try to solve the problem and make appropriate strategic cut. Yes? Well, CA, this method, by the way, this method is not universal. So you can solve most problems. It doesn't mean you can solve all the problems. For example, if you're only interested in calculating CA, for example, okay, how are you going to give the cut? You cut this way. That's fine. You cut this way. That's fine. You cut this way, and then you look at this side. That's become a joint. This is only the joint C. You cannot have 3 equations. Okay? Or I say you make this cut because you are interested in calculating AC, right? You make this cut. You make this cut, the structure is split in 2 parts, and then look at left side. You can solve the problem. But this is back to the method of joints, because when you make this cut, you are only look at joint A. And then, fortunately, there's only 2 members connected to joint A. Then you can still solve the problem. But this, in general, is called the method of joints. You can solve the problem. I'm not saying you cannot, but this is the special case at the previous method. So the bottom line is you can cut anything you like, as long as number 1 is a complete cut, and number 2, it helps you solve the problem. And I'll show you a little bit more with some kind of a little bit more challenging cases. I think I should have some slides. Okay, I'll show you how to make a strategic cut. Sometimes very difficult. I even cannot figure out. But if that's the case, most likely we're going to tell you how to cut. And once you get a cut, you should be able to solve for those forces. Okay, most problems you can make a simple cut, but the strategic. In other words, you need to cut those members you are interested in calculating the forces. Okay, so that's still the same problem, right? Okay, so for example, the same thing. You see here. We are interested in calculating those 3 members. That's why we make this cut, right? So then we solve the problem in general. I didn't talk about detail. In concept, we have 3 equations solving for 3 unknowns, right? But if you are saying, okay, can I cut this? Can I cut this one instead of vertically? Can I cut in a certain angle? The answer is yes. But you cannot solve the problem, especially for this one. It's difficult because you are cutting how many members? 1, 2, 3, 4. You are cutting 4 members. In general, if you are cutting 4 members, you're going to have 4 unknowns. Because when you cut each member, you're going to leave 1 unknown. That's called the force magnitude, right? So you cut it here, you get 1 unknown, cut here another unknown, cut here a third, cut here fourth. You have total 4 unknowns. Unfortunately, for 2-dimensional problems, you cannot have 4 equations. You only have 3 equations. So you can make the cut, but it doesn't help you solve the problem. That's why this cutting may not be a strategic cut. Okay? In other words, sometimes you can make this cut if you like. You can make this cut. See here? It's not a problem. As long as you can make a complete cut, the whole structure should split into 2 parts. That's the only requirement for making the cut. It's called a complete cut. But once you make complete cut, then you need to think about whether such cut help you solve the problem. And sometimes may not, and sometimes yes. And that's why sometimes when you make the curve cut, let me see if I have some, before later I will talk this one. Yes, see, I'm going to later on talk about some kind of challenging cut because I got it from the book. So by cutting something like this, and the special cases, you can easily solve the problem. But don't ask me why we can make this cut. We use a trial and error. We assume we make this cut, and then we solve the problem, and that's it. Don't ask me why we get this cut, because I even do not know. Okay? So back to this one, the metal sections, right? So this is the concept. Now I'm going to show you an example to demonstrate how we're going to apply the metal sections to solve problems. Of course, still trust problems. Okay?